All right, welcome to section 1.2, the calculus of parametric curves. We're not going to cover nearly all of this section. Mostly we're going to focus on this first learning objective to determine derivatives and equations of tangents for parametric curves. We're ignoring finding the area under a parametric curve, the arc length, and surface area for volume of revolution. Some of these are topics that we may return to later in the semester, but at the moment they're not really necessary. Let's go to the textbook again and just do a bit of a flyover. So if you go to section 1.2, you see this discussion of the derivative of a parametric set of equations, some examples. Then there's the second order derivatives, and then it continues on to integrals involving parametric equations. Stop here. This is as far as we're going. The big idea here is that even if you're given the equation of a curve parametrically, it's still possible to get slope and tangent line information and concavity information from the second derivative from the parametric forms directly. It's not necessary for you to convert them to, say, y equals f of x. The big difference here you'll find is that the derivatives that you generate will depend on the parameter t, not on x. And so you have to understand that the derivative dy dx as a function of t is telling you where on the curve as a function of t this particular slope is occurring. Let's go back to the text here. We'll do a few examples, but let me just point out sort of the generic idea here. Let's say you're given a parametric equation or parametric curve, x is a function of t, y is a function of t. Then you can find dy dx by taking the derivative of y with respect to t and dividing by the derivative of x with respect to t. Of course, this seems to beg the question that dy dx, that the function y equals f of x exists everywhere, and that's not necessarily true. We talked about this last time. Not all parametric curves can be expressed in the form y equals f of x, because not all parametric curves are functions in that they pass the vertical line test. Many parametric curves fail the vertical line test. For example, circles fail. So what does this actually mean, dy dx? It means like in a local place on the curve near a particular parameter value, the function can the curve can resemble a function. It can pass the vertical line test. Of course, there are places where that's not possible also, but that's kind of what we're talking about here. So it's dy dx assuming that we can describe a section of the curve as a function. We'll do some examples from the exercises in a minute, but this is a pretty typical exercise. Find dy dx for each of the parametrically defined curves and locate critical points on their respective graphs. So let's say we have x is equal to t squared minus 3 and y is equal to 2t minus 1 on the interval minus 3 to 4. We know that we can find dy dx by taking the derivative of y with respect to t and dividing by the derivative of x with respect to t. We can do that. The derivative of x with respect to t is 2t. We see that here, 2t. And the derivative of y with respect to t is 2. If we take y prime divided by x prime, we get 2 over 2t, which simplifies to 1 over t. And if we look at the curve, we see how this kind of corresponds to the slope on the curve. So for example, let's say t is equal to, I don't know, let's say t is equal to 0. What's the slope of the tangent line here? Well, it's vertical, so we would expect this to be undefined here. And indeed, if you do plug in t equals 0, which corresponds to this point, dy dx is undefined. In other places, for example, let's say at t equals 1, t equals 1 corresponds to the point -2 and 1, -2, 1. So that's here and here. This looks like a positive slope, maybe around 1. If we plug t equals 1 into dy dx, we see 1 over 1, and in fact dy dx is 1. So that's how this works. Remember that this is the xy plane. There's no t here. If we want to understand the slope of the curve here, we have to figure out what the t value corresponding to this point is, and then plug it in to the dy dx formula. Similarly, there's a formula for the second order derivative. We take the first derivative and we differentiate it again with respect to x, and that gives us the second derivative of y with respect to x. Since we know that dy dx has this form parametrically, it suffices to just take the derivative of this guy, and the resulting formula looks like this. So you take the parametric form of the derivative dy dx, you differentiate it again with respect to t, and you divide by the derivative of x with respect to t. We can see how that works in action. Let's again look at that same curve, t squared minus 3, 2t minus 1 on the interval -3 to 4. We first compute the derivative dy dx. From the last time, we know that that's 1 over t. And then we take that and we substitute it into the formula for d squared y dx squared. So that's 1 over t. Take the derivative with respect to time, that's negative t to the -2, divided by the derivative of x with respect to t. That simplifies to -1 over 2t cubed. With this, we can figure out the concavity of a particular section of the curve. For example, at t equals 1, we see that the second derivative is -1 over 2. So we would expect this section of the curve to be concave down. If we go up to the graph of this function back in the previous example, we know that t equals 1 corresponds to this point on the curve, and if you use your imagination, you can imagine that this section of the curve is bent downwards. It's concave down. Very good. All right, so those are the flyover examples. Let's look at some examples from the end of the section. So the first thing I want to look at is problem 65 from the end of the section. So that's right here. And the instructions for problem 65 are without eliminating the parameter, find the slope of each line. So notice that all of these parametric forms involve only t to the first power in both coordinates. So these all correspond to some kind of line, y equals mx plus b. So let's find the slope of each line. In particular, let's find the slope of exercise 65. Let's make a copy of that, stick it in here, and focus on how we can excuse me. Focus on how we can find the slope. Well, let's find the derivative of x with respect to t, x prime of t. is 5, y prime of t is 3, and dy dx is given by y prime over x prime. That's 3 over 5. So the slope of this line is a constant, it's 3/5. We could see this another way. The exercise doesn't require this, but just to convince you that this is actually a sensible result, we could eliminate the parameter here. So we could solve for t in terms of x in the first equation and substitute that into the second equation. And now we've eliminated t. And if you look carefully, the coefficient on x here is 3/5. And in fact, in mx plus b form, we know that the coefficient on x is the slope. So just by visual inspection, we can see that the slope here is 3/5, which confirms the earlier calculation. Let's try this again for another set of parametric equations. In this case, we'll look at problem 66. So in problem 66, find the equation of the tangent line at the given value of the parameter. All right. So to find the equation of the tangent line, we need two pieces of information. Indeed, for any line, we need two pieces of information. We need either a slope and a point on the line, or we need 2 points on the line. In this case, we're going to find the slope using the formula that we've just learned, and we're going to find a point on the curve. So what point corresponds to the parameter value t equals pi over 4? How do we figure that out? We plug pi over 4 into x and y and generate coordinates. So at t equals pi over 4, x of pi over 4 is 3 times root 2 over 2, and y of pi over 4 is 3 times root 2 over 2. Again, got to know your trig functions. So we know that the cosine of pi over 4 is root 2 over 2, and that the sine of pi over 4 is root 2 over 2. So this is the point that this line passes through, the tangent line passes through. What's the slope at that point on this curve? Let's compute x prime. That's 3 cosine t, and y prime, that's minus 3 sine t. And let's substitute the parameter value, pi over 4, to get 3 root 2 over 2, and negative 3 root 2 over 2. And remember that dy dx is given by the formula y prime over x prime at this location. So that's negative 3 root 2 over 2 divided by 3 root 2 over 2. That simplifies dramatically to negative 1. All right, so that's the slope of the line that we're interested in, the tangent line. Let's find the y equals mx plus b form of this. So we know that it passes through the point 3 root 2 over 2 comma 3 root 2 over 2. So the point slope form of this line, 3 root 2 over 2, y minus 3 root 2 over 2, equals the slope negative 1 times x minus 3 root 2 over 2. We can simplify this and put it into the mx plus b form. negative 1 times x plus 3 root 2, distributing that negative 1 into the parentheses, and then add 3 root 2 from the left-hand side, and simplify, negative x plus 3 root 2. That's the equation of the tangent line at this location. Does this make sense? Well, again, we didn't ask for this in the exercise, but notice this parameterization is really just a circle of radius 3. So let's give a quick sketch of a circle of radius 3. And what point on the circle corresponds to t equals pi over 4? It's actually this point right here. This is t equals pi over 4. And if it helps, that corresponds exactly to this angle, t equals pi over 4. Does the tangent line that we derived, negative x plus 3 root 2, does that look correct? Well, certainly this tangent line looks something like this. It definitely looks like it has a negative slope. Does it have a slope of negative 1? Sure. That seems to be legit. And is the y-intercept 3 root 2? Yeah, I'll give you that, right? We know that this point right here is 3 because the radius of the circle is 3. We know that root 2 is a little bit bigger than 1, so we would expect 3 root 2 to be bigger than 3. Sure, it all seems to hang together. Let's try another one. Let's try problem 86. All right, in problem 86, it's a little bit, got a couple of extra steps here. Find all the points on the curve at which there are vertical and horizontal tangents. Well, we know that vertical tangent lines correspond to places where the derivative is undefined, and horizontal tangent lines correspond to places where the derivative is 0. Notice in both of those cases, we need to find the derivative dy dx. So let's go back to our formula. We'll compute x prime. The derivative of t plus 4 with respect to t is just 1, and y prime. The derivative of t cubed minus 3t is just 3t squared minus 3. We'll compute dy dx as y prime over x prime, or 3t squared minus 3. Notice that dy dx is defined everywhere. So there are no vertical tangent lines. What about horizontal tangent lines? Well, in those cases, we're looking for places where dy dx equals 0, or in other words, where 3t squared minus 3 is equal to 0. If we solve that, we have 3t squared equals 3, t squared equals 1, t equals plus or minus 1. At these parameter values, the slope of the curve is horizontal. So we have horizontal tangent lines at t equals negative 1 and t equals 1. Does that seem plausible? Well, if you look at this equation, x is a linear function of t and y is a cubic function of t. If I were to eliminate the parameter here, I would essentially end up with y as some cubic function of x. Cubic functions typically have 3 roots, which means there are going to be 2 places between those 3 roots where the horizontal line, where the tangent line is horizontal. We can go over to Geogebra and convince ourselves of that. If we go to our friendly Geogebra calculator here and plug in the equations for this particular t plus 4 and t cubed minus 3t. All right, we have the equation of the curve over here. Let me put a point on there so that we can see the interaction. Oh, I used t instead of theta. All right, so I've built myself a little slider here that changes the parameter value. Since I'm using t up here, I'm using a different parameter variable here, calling it theta. And this moves the point along the curve. All right. My theta value here looks like it's pinned at 0, so I'm going to change that so that it can go along a range that I care about. So let's say minus 5 to 5. Oh, my Geogebra skills. Every time I hit tab, it moves to the next. Let's go back to this again. All right, one more time. Minus 5. There we go. Now we have positive and negative values. Why did I want that? Well, I'm interested in the 2 places where this thing has a horizontal tangent line. Notice right here, when theta is equal to -1, in our case, that was when t is equal to -1, we have a horizontal tangent line. That's t equals -1. The point on the curve is actually 3, 2. And then if I advance over to t equals 1, we get to the other extreme point on this curve, the local extreme, and that corresponds to the point 5, -2. So we are getting sensible results from these calculations. Let's do one more before we call it a day. So problem 98. Find the t intervals upon which the curve is concave up and or concave down. Let's grab a copy of this exercise. All right, well, if we're doing concave up and concave down, that means we need the second derivative. Let's first, we know that the first derivative is a necessary component of that, so let's grab the first derivative. So x prime is 6t, y prime is 3t squared minus 1, dy dx is y prime over x prime, like that. And we could simplify this a little bit, I suppose, to 1/2 t minus 1 over 6t, something like that. All right, remember now to find the second derivative, we need to compute the time derivative, or the parameter derivative, of dy dx up here, and then divide by x prime. Well, let's find the time derivative, the derivative with respect to time of dy dx. That's the derivative with respect to time of 1/2 t minus 1 over 6t. Continuing, the derivative of 1/2 t is just 1/2, and the derivative of negative 1 over 6t is 1 over 6t squared. All right. Continuing back over here with the second derivative, the numerator is now 1/2 1 over 6t squared, and we're going to divide by x prime, which is 6t. And when we're all said and done, we have 1 over 12t in the first term, plus 1 over 36t cubed in the second term. All right, find the intervals on which the curve is concave up and concave down. All right, well, concave up is where this curve is negative. If you're ever wondering, here's a nice mnemonic. Positive second derivative, concave up. Negative second derivative, concave down. All right, so let's find the places where this thing is positive. So the second derivative looks like this. What we need to do is figure out where it's positive and where it's negative. Probably the easiest thing to do here is to just ask yourself when it can be 0 and when it can be undefined, because those are places where a function can change sign. This thing, let me just remind everybody what we're looking at here. This is d squared y dx squared. Can this thing be 0? Well, neither of the terms independently can be 0. We have 1 over 12t, that can't be 0, and we have 1 over 36t cubed, that can't be 0. On the other hand, could they cancel each other out? Well, that would require them to have different signs, SIGN. And what we notice here is that this is positive when t is positive and negative when t is negative. And this is positive when t is positive and negative when t is negative. So in fact, the signs of these two terms agree for all t, at least for all t where it's defined. So they're never going to cancel each other. So this quantity can never be 0. So it can't change sign because of a 0. Can it change sign because of a place where it's undefined? Well, where is this thing undefined? It's undefined. So it's never 0, but it is undefined at t equals 0. So we can expect it to change sign, or we can allow for the possibility that it changes sign at t equals 0. So let's look at a number line. Here's t equals 0. And we can just test points, right? The only place it can change sign is at t equals 0. So let's look at t equals 1. Out here at t equals 1, we get a positive plus a positive. That's a positive. What about t equals negative 1? Well, we have a negative plus a negative, that's a negative. And so what we see here is a big dividing line at the place where this thing is undefined. So we can say definitively using our mnemonic, this thing is concave down here and concave up here. So we'll say it's concave down on the interval from minus infinity to 0 and concave up on the interval from 0 to infinity. And remember, these are t parameter intervals. Boy, this is pretty abstract. Can we kind of plot this thing and convince ourselves that what we're getting here makes sense? And the answer, of course, is yes. Let's go over to Geogebra. What I've done is I've plotted this parametric curve, 3t squared, t cubed minus t, and it looks like this. It's sort of this lovely ribbon kind of situation going on here. And I've got a point that's glued to the curve, and it moves around with parameter t. So let's look at t equals 0, which that's where we have the dividing line. And notice at t equals 0, we would expect some issues here. We have a vertical tangent line here, so the first derivative is undefined. Makes sense that the second derivative is also undefined there. Let's look at positive t's. So we move t a little bit to the right of 0, and look at the curve. We're now on this part of the curve. So as I moved away from 0, I went down below, and that certainly looks like it's concave up. So for positive t's, I'm down on this lower part of the ribbon, and it looks concave up. For negative t's, I'm on the upper part of the ribbon, and things look concave down. So remember, t is not in this picture. This is the xy plane. T is behind the scenes controlling things. And when t is positive, the curve is concave up. And when t is negative, the curve is concave down. That's how we interpret this information. All right, let's wrap this up here. So if you go back to the textbook here, I just want to emphasize that we're only interested in computing the first and second derivatives of parametric curves, which gets me up to just about 99. And then problem 100 on starts talking about integration and other things that we're not going to talk about in this particular section. And finally, once you've worked on enough of these exercises to feel comfortable with the material, I want you to go over to WebWork and do the assessment for Chapter 1, Section 2. Thanks.